This is my submission for 3 Blue 1 Brown Summer of Math Exposition, and today I'm going to be doing a proof of Euler's identity by differentiation. Now, if you're not familiar with Euler's identity, it's just that e to the power of pi times I plus 1 is equal to 0, or that e is equal to negative, e to the power of pi times I is equal to negative 1. Okay. So before we can start proving this, we're going to have to talk about complex numbers a little. So if we talk about complex numbers, we can say any complex number z, okay, let's call it any complex number z, can be written as x plus I times y. Okay. You may have seen this as any complex number can be written as a plus I times b, which is what we call rectangular form. Okay. We're going to use x and y. It's the same thing, but we're using x and y so that we can draw a graph. Okay. So if we were to graph like this, if we were to graph x and y, we'd have some distance x over and some distance y up. Okay. Then we'd have a distance, we could connect them by the distance, and we'll call this distance r. And we'd have some angle between them, and we can call that angle theta. Okay? So now, with this, what we can do is we can use trig functions of theta to start relating these things. So, what I mean by that is, like, we can take sine of theta. And sine of theta, sine is nothing but opposite over hypotenuse, which is just y over r. And cosine of theta is nothing but adjacent over hypotenuse, which is just x over r. If we multiply r to both sides, we can isolate y and x, and we can get r sine theta is nothing but y, and r cosine theta is nothing but x, like this. Okay? And why are we doing that? Well, we're doing this so that we can substitute in r cosine theta and r sine theta into x and y here, and we can say that now any complex number z can be written as x, which is r cosine theta, plus I times y, which is r sine theta. Okay? And now that we have this, we can factor out an r from both. We're going to get any complex number z can be written as r times cosine theta plus I sine theta. Okay. And this is going to be really important. Okay, you might notice this, what we would call like polar form. So if you have a complex number and it's written in this fashion, where r and theta could be anything, we'd say it's in polar form. Or we can write polar form in another way using e, which we'll get to later. So any complex number can be written like this. Let's look at a specific complex number. We're going to be looking at e to the power of I, and instead of at pi, so trying to prove what e to the power of I times pi is difficult because there's two irrationals and an imaginary number, right? It's hard to prove that's equal to negative 1. But if we do something like e to the power of I times x, where x can be anything, x is just a more general form, if we can figure out information about this, and then we can put in pi, we can try to prove that. So e to the power of I times x, we don't know much about this number, but we do know that it belongs to the complex plane, right? No matter what number we put into x, we're never going to leave our complex world, okay? It's going to have some real part, and it's going to have some imaginary part, which is what a complex number is. Okay. So we can say that e to the power of I times x belongs to the set of all complex numbers, or epsilon c. Okay. What that also means is that we can say e to the power of I times x can be written as this, r cosine theta plus I sine theta, because e to the power of I times x is a complex number, and all complex numbers can be written this way. Now, that doesn't mean that we can write any complex number as e to the power of I times x. We don't actually know that. all we do know is that e to the ix can be written as a complex number. Or it is a complex number, so it can be written like this. So r and theta, therefore, must be functions of x, right? As x changes, r and theta are going to change, okay? So, instead of writing r and theta, what we can do is we can say, instead of r, we're going to write r of x, and instead of theta, we're just going to write theta of x, okay? So now what we're saying is that on the left here, if we put in any function, or any value for r, or x, there's some function r, that we can put in that x and get back value for r, and we can put that here. And for any value x here, we can put that into our function of theta, and put that over here, and it would make both sides equal. Okay, that's what we're saying. So we're going to rewrite it like that. We're going to say e to the ix can be written as r of x times cosine of theta of x plus I sine theta of x. Okay. Now, why are we writing r and theta as functions of x? Well, there are a couple reasons. The first reason is what we already talked about. E to the ix belongs to a set of all complex numbers, so it can be written like this. But it is not necessarily able to be any complex number, so this isn't really equal to this. Okay. So we're writing it in this way as functions of x to show this has to be within the range of x. We're also doing it because this isn't a proof by differentiation. So when differentiating r and theta, well, they're not necessarily constants, so it's difficult to differentiate them, because we can't differentiate them like constants. Writing them as functions of x when differentiating in respect to x makes things a lot easier. Okay, and we'll see why in a second. So we'll just write, now we're just going to differentiate both sides, so we'll do d over dx. Like that. Okay? And now let's just differentiate. Differentiating e to the ix. Well, we'll just use chain rule here, right? So to differentiate this, we just take the inside function, which is I to the x. Differentiating that, we're just going to get our constant back, which is I. Differentiating e to the x is just e to the x. So we just write e, and then we keep the inside function the same. So d over d of x of e to the ix is I e to the ix. Okay? We can say this is equal to the derivative of this. We're going to have to use product rule. Product rule is just that the derivative of some function of x times another function of x is just the derivative of the first function times the second function, plus the derivative of the second function times the first function. That'll make a little more sense as we go through this. So first thing is the derivative of the first function. What is the derivative of r of x in respect to x? Well, we're just going to get r prime of x. And I'm just going to write r prime to save space. R prime. And then we just leave this part the same. Cosine theta. I'm not even going to write of x. Just, it doesn't really matter if we use r, theta, or r prime of x, theta prime of x, whatever. Just save space, we're going to keep out the x. Plus I sine theta. And then we go plus, we keep this part the same this time, so it's just r, times the derivative of this. So the derivative of this, we're going to have to use chain rule again. So looking just at the first term, cosine theta, the derivative of cosine theta of x in respect to x. Well, derivative of cosine is negative sine, so we'll just put our negative down. Chain rule, we have to take the derivative of theta of x, which is just going to be theta prime, same reason as r prime. Then derivative of cosine, we said was negative sine, so we'll just put down sine and then theta. Plus I is a constant, so it'll stay there. Derivative of sine is just cosine, so that's why it's a plus. Derivative of theta is theta prime, and then derivative of sine is just cosine, keeping the inside part the same. So now we have this, okay? And why do we do this? Seems like we got a lot more complicated, right? Well, the reason is we're going to want to be able to separate real parts from imaginary parts. It's still a little difficult to do, so let's try to simplify things a little bit. And the way we're going to do that, well, let's look at the left side first. It's hard to kind of split up real and imaginary parts right now. So let's try to find a way we can rewrite this. Well, if we think about it, what is e to the ix equal to? E to the ix is equal to nothing but this thing here, r cosine theta plus I sine theta. So we can say on the left we should have I times r cosine theta plus I sine theta, like this. Okay, and I'm actually going to just distribute here. So on the left we're going to have, distribute this to the second term first, just because I times I is going to give us a negative, real number. I times I is negative, r sine theta plus IR cosine theta. Okay, so all we did was we substituted this back into e to the ix. We got this, and then we just distributed through and got this. And this is equal to, we're just going to distribute these things. So we're going to distribute r prime to here and r to here. Distributing r prime to here, we're going to get r prime cosine theta plus r prime I sine theta. Okay. Plus, we're going to get theta prime, I'm just going to write r primes first, theta prime times negative r sine theta plus theta prime times IR cosine theta. Right, so I just distributed r to this. You'll see why I kept out r theta primes out front. Okay, so now we've done this. So now that we have all these separate terms, we can match up our real and our imaginary parts. It's the same kind of concept as partial fraction decomposition, where we could match up some terms with A and some terms with B, and then solve for A and solve for B. If you don't know what partial fraction decomposition is, we're not going to be doing that, but if you are familiar with it, it's the same kind of concept. So let's do that. We're going to be taking, if you see, negative r sine theta, that is real, it has no i's. IR cosine theta is imaginary. R prime cosine theta is real. This is imaginary. This is real. And this is imaginary. Right? So all the terms with I in it, I've just underlined in blue. All of the terms without I, I've underlined in black. And now let's just set these equal to each other. So we'll get negative r sine theta on the left, right? And this is going to be equal to r prime cosine theta plus theta prime negative r sine theta. Okay? I'm going to leave a little room here. You'll see why in a second. Is equal to r prime cosine theta plus theta prime negative r sine theta. That. Okay? So now if you'll notice, and I'm actually not going to set the imaginary parts equal to each other. We could do the same exact thing as we're doing here with the real numbers with the imaginary numbers. But if we did, we'd actually get the same exact results, and that's fine not. If you'd like to go through and set them equal to each other and prove that to yourself, it's fine. I actually suggest it, but just to save some time and space, we're not going to be setting the imaginary parts equal to each other. Okay, so now we have this. And if you'll notice, we have a sine part here and a sine part here. And we have a cosine part here, and we don't have any cosine part here. But really what we can say is that on this side, we have 0 cosines of theta, okay? And why are we doing that? Because now we can do the exact same thing we did here with real and imaginary terms. We can set our sines equal to each other, we can set our cosines equal to each other, okay? So we can say negative r sine theta, we're going to set that equal to theta prime negative r sine theta. And we're going to take 0 cosine theta and set that equal to r prime cosine theta. Now, if you'll notice, with both of these, something really nice happens, right? Over here, negative r sine thetas will just cancel out, and we'll be left with 1 is equal to theta prime. And on this side, our cosine thetas will cancel out, and we'll get 0 is equal to r prime. Okay, so now we just need to think about derivatives and how they work, what they mean. Well, think about if you have a derivative, let's look at this one first. If you have a derivative and it's 0, okay? Think about the graph of r of x, okay? That means that on original r of x, we have a slope of 0. We don't know where it is, but we know our line is a slope of 0. So maybe it could be here, it could be up here. We don't know, but we know it has a slope of 0. And what does that mean? Well, it means that original r of x, is just some constant, but we don't know what value we have for that constant. So we can say r is equal to some constant, we're going to call it c1. Let's look at theta prime. So on our original graph, just theta of x, we have a slope of 1, right? So we know our line's going to have a slope of 1. So maybe it looks like this, maybe it looks like that, or maybe it's down here. We don't know which line it is, but we know it has a slope of 1. We just don't know how high or low it is, just like this here. So we know that our original function theta is just equal to slope of 1 is x, plus some constant c2, because we don't know where it is. Okay? So this is what we know. Theta prime and r prime have now told us that r is just some constant, and theta is just x plus some constant. So now what can we do with that? Well, imagine if we test x at a specific point, and we got information back about r and theta, or about our constants. Well, in that case, because they're constants, and it doesn't matter what value x is, we can just plug them into those formulas and get more information. We'll see exactly what I'm talking about in a second. But let's just do that. Let's test x at a specific point. And when are we going to test x at? Well, the easiest place to test x at is just 0. So we're just going to test x at 0, when x is 0. Okay. So let's do that. And what equation are we going to use? The easiest equation, or the equation that's going to help us the most, is going to be an equation with x in it, obviously, because we're testing x, an equation with r in it, and an equation with theta in it, and we also don't want there to be any theta primes and any r primes, because it would just make things more difficult, more complicated. So what equation has x, r, and theta in it, and no derivatives, no prime functions? Well, just our original equation, right? So let's use that. So we'll go e to the power of I times x, where x is just 0, is equal to r times cosine theta plus I sine theta. Okay? Now, if this is the case, well, obviously on the left, e to the power of I times 0, e to the power of 0, that's just 1. Now we get 1 is equal to r cosine theta plus I sine theta. Now notice on the left side we have a real number. There's no complex or no imaginary part. On the right, we have this imaginary part, I sine theta. So we need to get rid of that somehow, because if this has any value, right, if that has any value, then we're going to have an imaginary part, and they won't be equal to each other. So what we can say is when x is equal to 0, I sine theta is equal to 0, which means that sine theta is equal to 0. So when is sine theta equal to 0? Well, let's look at a unit circle. Okay? Now if you remember from trig, sine is nothing but x value, and sine is nothing but y value, rather, and cosine is nothing but x value. Like that, okay? So we're saying on our unit circle, when is y value 0? Well, the easiest place is just right here. 0 radians over, because it's 0 radians, this is pi over 2 radians, not delta, pi over 2, or gamma. This is pi, this is 3 pi over 2, and then this can also be 2 pi. But 0 radians around, we have a point at 1, 0. And y value is 0, therefore we can say sine theta is equal to 0, so theta is equal to 0. When x is 0, theta is equal to 0. Okay, so let's write that. We'll write 1 on this side is equal to r cosine 0 plus I sine 0. I sine 0, we just said, is 0. That's the whole reason that we chose 0. Cosine 0 is nothing but x value, and x value is 1. So now we have 1 is equal to r times 1, so r is just equal to 1. And if you remember, r is a constant. In all situations, it's going to stay the same, so r is always equal to 1. Okay, we've solved for r. Okay, so now we've done this. Now, remember, when x is 0, theta is equal to 0. So we can take those and plug them into our equation for theta, right? Theta is equal to 0, so we'll write 0 is equal to x, which is 0, plus c2. Therefore, c2 is equal to 0. And then if we plug 0 into this equation, we'll get theta is equal to x. In fact, so r is equal to 1 and theta is equal to x in all situations. Okay, so now we're going to rewrite our original function one more time. We'll get e to the power of I times x is equal to r is 1 and we're multiplying to everything surrounding, I'm going to write it, is equal to cosine of theta, but theta is nothing but x, plus I sine of x, right, instead of theta. And this here is actually Euler's formula. Okay, e to the ix is equal to cosine x plus I sine x. And we're going to be using it to prove Euler's identity. So how are we going to do that? Well, think about when e to the power of I times x belongs to the set of all real numbers, epsilon r, right? When e to the power of ix belongs to the set of all real numbers, just like before, sine x must be equal to 0, because we need this to be gone, okay? Which means that, so sine x must be equal to 0, what does x have to be equal to? Well, we could use 0 radians around again, but what would that do? It would put 1 on this side like before, and we'd get 1 on this side. Okay? And that's not really what we're looking for. Instead, let's try to find another point where y value is 0, where sine x is 0, to get something more interesting. So we're also going to need a circle. Well, right here, we also have a point of negative 1, 0, right? So, if that's the case, then we can also say, when e to the ix belongs to all real numbers, sin x equals 0, we can just say that x is equal to pi. Okay? And now let's plug that in. We'll get e to the power of I times pi is equal to the cosine of pi plus I sine pi. Well, we just said I sine pi is 0. And cosine pi is nothing but x value, which is negative 1. So we'll get e to the power of I times pi is equal to negative 1, or e to the power of I times pi plus 1 is equal to 0. And there is Euler's identity. But we can actually do better than this. Okay? So notice how we just need to get to this point. But just like how this is 0 or 2 pi, here we could go around another 2 pi, right? We could go here, pi over, and then we could go around another 2 pi, and we'd still end up on the same spot. Or we could go backwards 2 pi, like that, and so end up on the same spot. So, for pi, what we can do is we can say e to the power of I times, we have to start at pi, plus or minus 2 pi n, where n is any integer, is equal to negative 1. Like that. So now we've not only proved Euler's identity, but we've come up with a more general form. There's actually an infinite number of solutions to, I guess what you could say, is e to the power of ix equals -1. There's an infinite number of solutions. So that's a more general form of Euler's identity proved by differentiation.